Good afternoon. It's now noon, and I guess I was told it would be a good time to start. So I guess I'm going to introduce myself, and I'm Ed Sandor. I'm the Applications Engineering Manager from Taconic, and also Chairman of the IPC Microwave and High-Speed Digital sector. And so I'm a microwave engineer, so I'm electrical engineer by education. And I give a lot of presentations to companies, but mostly the microwave guys. You know, those are the weird guys that sit in the room and do the microwave stuff, like George and Dimitri and the guys. But so what I did is I modified this presentation a little bit because I figured maybe all you guys really aren't interested in all the intricacies of microwave materials. And so this is a newer presentation that I'm giving. But anyway, I'm going to start. And by the way, at any time, if you want to interrupt with a question, it's not a canned presentation. I'll also specify this. I give a lot of classes, and I actually have about, I think I give, it's a 12-hour class over 2 days on microwave technology. And so, so I have a lot of stuff. And so I certainly can't share it all with you because you don't have the time and I don't have the voice. But if you do have questions, I've got a lot of information here, and hopefully I can share and answer some questions if you have it. So introductions, I think I just did that a little bit. I'm the Applications Engineering Manager. Let me tell you a little bit about Taconic, and so you get a little feel of the company, what we do. We are the largest user of Teflon in the United States, actually in the world probably, when you look at it. And Taconic, we buy tremendous amounts of polytetrafluoroethylene, and what we do is we coat that Teflon onto products. And so, guys, if you guys are familiar with the like the Metrodome roof in Minneapolis or the Denver airport roof, it's a Teflon fabric. We make that. It's called architectural fabrics. We make significant volumes of that over in Europe, mostly. Industrial products is, again, woven glass coated with Teflon on it. We are a very large supplier to the food industry. In fact, our largest customer in the world is McDonald's. And they use it on their grills for a couple of days, and they throw it away and then replace it with another piece of our material. And I think we supply 60% of the McDonald's in the world use our material. I work for the Advanced Dielectric division, which is the printed circuit board division. And what we're doing is taking woven glass Teflon, mixing things with it, and then putting copper on it, and we sell it to you. And actually, Harris Broadcast, or GatesAir now, is still one of our top 10 customers in the world, when all the materials that this company buys from Taconic. This little map shows where some of our plants are located. And so, you know, our headquarters is in New York, and we have manufacturing in Brazil, and we have 4 plants in South Korea. We have locations in China, Europe, the United States. So we're not a little company, but we're privately owned. And the owner is Andy Russell, and he does not believe in advertising, so you don't typically see us in all the advertising in all the trade magazines. I put this last, but I'm going to put it first now. What our advantage in the industry when you look at our materials is that we can typically turn materials around in very, very quick time. So we have a 5 to 10 day lead time, and we actually do a lot of developing of new materials. And we give away large samples, 18 by 24, so you guys can build many, many samples on one of our sample panels. And we do stock materials, and I believe you guys you stock our materials in some of your labs here, and also in Quincy. Technical support, which is a given. And then what I wanted to do is also, just because it's important, I wanted to cover what the IPC is. And you guys, when you're doing your prints and doing your designs, you're always specifying that the board has to be built to IPC 6018. The board has to be, all the drawings have to be to IPC standards. And so the IPC is, we write all the standards. And I'm chairman of the whole high frequency and digital group, which includes all the design guides, material testing, all the bare boards, you know, how you build the boards and all the quality requirements and all the coupons that are required on the boards, as well as the material specs, and then all the ways how to test the boards and test materials. And so I have about 13 committees that report to me at IPC, and I'm also on the IPC's Technical Advisory Committee, which dictates the direction of what we're going to do in the industry at the IPC. But you guys use it a lot, whether you know it, but it's on every single one of your prints. You probably have 15 notes which specify IPC standards or IPC documents. So what I did on this is, rather than just talk about what we do at Taconic, I thought I'd maybe try to break down materials. So for example, this says what commercially available resin systems. And so when you guys, when you open your computer and you look at there's a printed circuit board in there, what material is being used? Or if you're opening up, one of your cabinets, what material is being used on the power amplifier? And so what I thought I'd do is just give you an idea of all the different materials that are available in the marketplace. And so I actually broke them down generically, but I'm breaking them down by electrical properties as well as then mechanical properties of those materials. And so, one of the big things that we look for in our industry is the dielectric constant of the material. And the dielectric constant of a material really determines how fast the signal, or how fast, I guess I'll say the signal is going to propagate on the board, how fast it's going to get from point A to point B. And so the lower the dielectric constant of a material, the faster the signal will propagate down the trace. So we want, I put all these little things up here, faster signal propagation, lower signal loss. By picking a impedance that you're going to use on the board, you can determine, a 50 ohm line is going to be X mils wide, and you're going to have a nice clean signal. And then by changing the dielectric constant of a board, you can change the size of the board. So for example, if you're doing something on FR4, which is epoxy glass, it's got a dielectric constant of about 4.5. Your traces may be, I'm going to say probably 25 mils wide. But if you want to get the same electrical performance, you could actually go to a dielectric constant of 10, and you can shrink the board down to half the size and get the same electrical performance. So the dielectric constant, I think I put here, higher decay is desirable in some applications when you want to reduce the size of the circuit. So by going to a higher dielectric constant, you can shrink the size of your board. And it may not be important on broadcast equipment, but if you think about it on a jet aircraft, all the equipment that's in the cockpit, they do everything in high dielectric constant because they have a limited amount of space. So all their boards are actually on a dielectric constant of 10, so they can shrink everything down to fit it all into the cockpit. So, again, what I just did here is I just putting down all the different materials that I could think of that are being used today in the industry. And, and our product is basically the PTFE glass is the Taconic products. What we're doing is taking glass fabric and we're coating Teflon onto it, or polytetrafluoroethylene. And by putting just PTFE in glass, you can see we get a dielectric constant of 2.2 up to 3.5. If we put some ceramics in it, we can actually change the electrical dielectric constant from 3 to 3.5, and you actually change the mechanical properties by putting different fillers in there. And then, there's some people that manufacture hydrocarbon ceramics, and those are, again, a completely different resin system, but by sticking different things in there, you get a dielectric constant 3.4, 3.5, and actually now people are starting to make higher dielectric constants with the hydrocarbon ceramics. But again, I don't know how, my point would be on this is to show that there's a lot of choices that an engineer has on picking a material for a particular printed circuit board. Now, there's one interesting thing here. I put over here on this little chart on the side, on the, what would that be, the right-hand side, where it talks about test frequency. And that, because these are my committees at IPC, when for testing of materials, there's really only 2 recognized test methods for testing electrical properties on material. And one is at 1 megahertz, and the other one is at 10 gigahertz. And so when somebody else says, well, we're building equipment at 800 megahertz, and what's the dielectric constant? We can guess, but the actual test methods, there's only 2 that are recognized, 1 megahertz and 10 gigahertz. Now, guys, if you're actually looking at the screen, you'll sit there and say, well, wait a second, you have a polyphenylene ethylene at 1 gigahertz. Well, what they're doing, and that's what they put on their data sheet, but what they're doing is extrapolating and saying, well, this is what we're guessing it's going to be. And then they test it the same way, and so that's what they put on their data sheet. But so typically when you pick up a data sheet, all you're going to find is a 1 megahertz value, which is accurate, or a 10 gigahertz value. Anything else in between, it's, I guess I'll say we're either extrapolating or coming up with a modified test method, but it's not to be used for apples and apples comparison, because a different company may not use the same test method to test it at 1 gigahertz. The other feature of any electrical material is the loss tangent, dissipation factor, tangent delta. But what that means is it basically has to do with the percentage of signal that is lost as the current is going down the trace. So if you think about how electromagnetic energy works on a printed circuit board, is the fields are generated from the ground plane and they go up to the trace. And as the fields are going through the material, some of that signal gets lost, some of the fields get lost. And so the dissipation factor basically would be, I'm going to call it a percentage of energy that is used to push the current down the trace. And so the lower the loss, the more of the signal gets propagated. The higher the loss, the less signal is propagated. And so there's all different types of dielectric dissipation factors in the material. And like I said, it preserves the signal strength and the integrity. And so again, I'll switch over to this and look at these same type of materials. And so when you look at this, and these are ranges, I guess, when you sit there and say the PTFE glass material is it is the best. When you look at it, with a dissipation factor of 0.00009. That means that the fields that are going through the material, you're only losing 0.09% of the signal or the fields going through the material. By the way, where does that go? It generates heat. It's one of the losses that you'll find. It will be generating heat. When you start sticking other things into pure Teflon, the losses go up a little bit because you're sticking something else in there. So when you go into a ceramic decay, the second one down, PTFE ceramic, you can see that the losses go up where you're now losing 0.12% of the fields through the material. Now, if you keep on going, you sit there and say, wow, what is FR4? A regular epoxy glass. And you go down to the bottom, and there's a couple different grades of FR4, and I'm going to come back to this and talk about this in a little bit. But you can look at it and you'll say, damn, 0.025. That means 2.5% of the signal, and not 0.2, but 2.5% of the fields actually get lost in the material as the signal is, as the signal is going down the trace. So it actually, ends up with a lot of loss, which we all hate in our microwave boards because that contributes to very, very poor board performance. But again, looking at all these different materials, an engineer has a lot of different choices when he's doing a design. And what you do is you play a lot with, I call it trade-offs, because when you look at prices, I think it also works the same way. The materials at the bottom of this chart are probably the cheaper ones. And as you go up to the top, you can actually get to some of those materials on the top, which are 5 to 10 times the price of the ones on the bottom. So there's a big trade-off on materials. Okay, now the other thing, next thing is I call it properties of material, glass transition temperature. And this is, I put the definition here. And I don't know if you guys want to read it. I don't want to read it, but you can read it from where you're sitting. But basically what it is, this is what I always talk about it, is all materials have a coefficient of thermal expansion. So when you heat them up, they expand a little bit. There's a certain point where typically it's a linear function. So it's linear up to a certain point. Once it gets to a certain point, which is the glass transition temperature, the expansion in that material significantly increases. So for example, I'll go back to this past slide. I'm going to switch back here and say, on the bottom two materials, multifunctional epoxy and difunctional epoxy, they have different TGs, which means that, I'll switch ahead now, and I'm going to switch ahead and say, this is glass transition temperatures of different materials. And so that means, like, for example, the first one, hydrocarbon ceramic, it actually can go up to 280 degrees C with a linear expansion, And then above 280 degrees C, then something else happens. Typically, the expansion goes up maybe five times the rate. And so you sit there and say 280 degrees C, we're never going to see a board that hot. And so typically, these are very good materials to use for high, for high T sub G for a lot of different designs. By the way, if you look at it, all those materials on the top are, I'm going to say, more exotic materials. Typically, when we're building boards or your typical FR4 materials, you're typically looking at multifunctional epoxy or difunctional epoxies. And what they have, you look over here and you'll say 130 degree T sub G or 140 degree T sub G. That means that the material has a linear expansion up to that point. Then above 130 degrees, then the expansion goes up very, very significantly, like 5 times. What does that mean? It used to be you could take that board and you could put the components on it, run it through an IR reflow, and the board would come out the other end with all the components soldered in place, because you're exposing it to a 210 degrees for how many seconds over the IR reflow. With the ROHS and lead-free solders, now we're looking at 280 degrees. And if you take a material that's made out of a difunctional epoxy and you run it with a T sub G of 130, you run it at 280 or 290 degrees centigrade, that material is going to bow, twist, and warp, and virtually could actually fall apart because, again, the material's not made to stand up to those temperatures. So what we've seen in the last couple of years, as more and more companies have been forced to go to lead-free applications, we've seen the difunctional epoxies basically are disappearing from the market because they won't stand up to the higher temperatures of the IR, the soldering requirements for ROHS applications. Notice I put on the bottom 2 materials. Teflon materials typically, they don't melt. That's one thing about Teflon. Teflon gets softer as it gets very, very hot, but it doesn't actually melt and flow. So its CTE doesn't really change. And so its actual glass transition temperature is something like 30 degrees centigrade, which doesn't make sense because that's actually room temperature or colder. But so typically these materials could be used up to very, very high temperatures without worrying about the T sub G of the materials. So we always put in there NA, not applicable, because if we put down the real number that you do by all these DSC testings and different types of testing, the number sometimes scares people to use it because they say it's very low. But again, it doesn't melt, so it doesn't flow, so we don't have an issue with the T sub G, actual TC temperatures on Teflon materials. Oops. Okay. We just talked a little bit about CTE, and I think that more or less relates to the plated through holes in the material. And so the lower the CTE of the material, the better. That's the best way to look at it. And so again, looking at all these different materials. By the way, the way I put this chart together, you can see I put down 2 numbers, the CTE up to the T sub G, coefficient of thermal expansion up to the glass transition temperature, and then another number for above the glass transition temperature. And again, you can see PTFE is the first one, PTFE ceramics. It really doesn't change, neither does the PTFE glass materials. They don't change. But you look at a lot of these other materials, there's a difference below, actually, okay, this was below the T sub G and this one's above the T sub G. But you can see it expands at 85 parts, this looking at the difunctional. 85 parts per million per degree C below the T sub G, and it could be as high as 215 parts per million once it gets above the T sub G of the material. So, but every material has a thermal expansion, and so this just represents the different materials' thermal expansion below and above the T sub G of the material. With the new lead-free requirements, it's amazing that a lot of people are getting away from the traditional FR4s, the epoxies materials, and a lot of people are going to the BT epoxies, bismelamine triazines, or a lot more people are going to the polyimide because it will stand up to the lead-free requirements. Thermal conductivity. What does that give you on a board? Well, you know, the board runs cooler. You get higher packaging density. You can put more components on the board since you can actually run it cooler. The interesting thing about thermal conductivity is that all of these materials, printed circuit board materials, in my opinion, they're all insulators because copper has a thermal conductivity of like 390 watts per meter per degree Kelvin. 390, just remember that number. And then I'm going to flip to the next page and I'll show you our numbers on all of our printed circuit board materials. So think about 390 watts per meter, and you know, even the Teflon materials are, you know, PTFE glass, it's 0.25. So when you really look at it, we're insulating. You know, we're really not doing much thermal conductivity between, you know, in the printed circuit board materials. But some people find that, hey, if you can take a thermal conductivity of this material and have it at, you know, 0.27, if you can raise it up to 1, our board's going to run cooler. And so we've been doing a lot of work on raising up thermal conductivity, but I still sit there and look at it and say, it's still an insulator. I don't care, 1 watt per meter per degree Kelvin is nothing compared to the actual copper on the board, which is, you know, dissipating energy at 390 watts per meter per degree Kelvin. I think brass is probably, I think brass is probably close to 300 degrees, 300 parts per million per degree C, and aluminum is down into the 190 parts. So, you know, our materials are really, like I said, I think I call them, you know, insulators. But moisture and chemical absorption. That's another very, very important mechanical property on the material. You think about it, when we make the material, we're shipping it to a printed circuit board shop, and those guys are cleaning it. They're cleaning it with chemistries, they're cleaning it with water, then they're going and putting masks on the board material, and they're etching it so that it's exposed to all different chemistries. Then they're drilling holes to it through the material, then they're putting that into processing in order to plate the holes. So all these materials see a tremendous amount of chemistries when they're being manufactured. And so, and by the way, this is one of those things that I find amusing, because there is no such thing on a data sheet of chemical absorption. Everybody's data sheet talks about moisture absorption, which is basically water. And so most of these materials have water absorptions which are pretty low. I mean, you look at the first one there, PTFE glass, we're looking at, you know, 0.015%, which means it's not going to pick up any moisture. But you go and you look at it, like, for example, where's polyimide on here? Polyimide glass, 0.8%, which is pretty high. You know, that's a very high moisture content. So the board shop, or even you guys, when you're assembling these things, have to put these boards through a bake cycle to try to bake out any residual moisture that may be stuck in the board before you do other things to it, because you don't want the board to explode. It has a lot of moisture in it when you expose it to IR reflow, or in your situation where you're having high power running through these boards and they're getting really hot. But what's interesting is that water absorption is only one part of it, and it's on the data sheet. It says moisture absorption is whatever the number is, but there's no way to predict the chemical absorption. And some of these materials will pick up chemistries like you wouldn't believe. They won't pick up water, but they'll pick up the trichlor, all the different plating solutions. And I tell you what, we have a lot of issues in our industry when people are using materials and they don't properly rinse and bake the materials. And I always tell people when they're building the boards, anytime you're in doubt on what chemistries you're exposing a material to, take that board before you put it in the next process, rinse it in hot deionized water, and then rinse it in alcohol, and that'll remove the organics and inorganics so they aren't penetrating the material. Because what happens is you can expose it to chemistries, and then you go into the next process, and you can actually seal in those chemistries that you saw prior. And which, by the way, you're not going to see until you guys heat the board up, and all of a sudden you'll see the copper's blistering off. you know, or you'll see something happening where you'll see a lot of warpage in the board, you know, because just things are happening in the materials. You know, actually those, well, I'm going to changing the subject here because those are the, I call it the key material properties that I think we all look at. You know, there's certainly the thickness and the type of copper, but when you're actually looking at the raw materials, those, the dielectric constant, dissipation factor, moisture absorption, CTE, T sub G, those are the critical factors that we engineers use to actually pick a material that we're going to use on our designs. What I just did here is I actually put some things together and said, okay, what materials have you guys been using from us for the last, gosh, 20 some years? I don't know, it's been a long time. And we have some of our materials, so these are actually, it's a lower dielectric constant. You actually buy a lot of it. It's a TLX material, which is got a 2.5 DK material. And so the second one down on the list, we have a lot of applications. And these materials have been around since the 1960s. And typically those materials are very simple. The dielectric constant of the material is controlled by the amount of glass weave we have in the material and the amount of Teflon that's coated on the glass. Then we put copper on it. So it's very, by the way, maybe I can even stop and ask if you had any questions on the stuff we prior covered. I don't know if anybody has any questions. Somebody.
I have one.
Thank you.
You mentioned that the polyimide material is becoming more popular for Ross type applications. Yet on a couple later charts, it had a high moisture absorption ratio. It's like
a lot of moisture. Yeah.
You know, it's like, well, that's a good material for this, but it's bad for that. But I guess my real question was, coming for this ROHS,
right,
which we have to pay attention to. What's the cost impact?
That's it's a good question, and I don't know if I have an answer to that because the verdict is still out. There are companies now. When ROHS, Rosie, I don't know, there's all different pronunciations you can say, Rosh, but when that first came out and said we have to eliminate the lead in the solder, so we all had to shift from basically tin lead solder to a lead-free solder, and the telecommunications industry was exempt. And then military was also exempt because anything that dealing with national security, telecommunications is, you know, supposedly national security. And so they were exempt for years. And so a lot of those companies ignored it because they said, you know what, there's no alternative. There's no good alternative. There are some companies now that I'm working with, even though they're required to, they're saying we cannot build a good enough product that will meet the military's life requirements without using tin lead solder. And so they are actually going back and saying, I don't care what you say, we can't do it because we have proved that there's no good alternative to tin lead solder. And so also the telecommunications company is now having problems with finding alternatives. You know, everybody's trying to meet the requirements, but I'll tell you, yeah, it's very, very costly, but I don't think I have a number on it.
Okay, that's like, you know, a board of X size in glass is, you know, $4.
Mm-hmm.
Specify that material, $40, $400, $8, you know.
Yeah, well, right, and well, my aspect or my view of it is prior to that, since I'm a materials guy, so I'm the guy on the bottom who's supplying the material to the different shops, and so what I think though is that there's a lot of work that is being done by the big guys, and I'm thinking the Lockheed Martins, the Northrop Grumman's, the GDs, where they're actually analyzing what effect the alternatives have on the board design, and then they're imposing their requirements on the board shop. Now, whether the board shop has that in-house or whether they have to put a new line in to meet those requirements, that's where I think the big cost factors come in, because the board shops are all different as far as their capabilities. And so, you know, I know we try to stay on top of it, but I'll tell you, it's a very complicated issue with the, you know, lead-free issues. And I'm not sure I can give you a number if it adds 10% of the cost of the board or 22%.
General idea. That's
I think Ed, he was asking more polyimide.
Well, he specified that, right? And
not the rose.
Well, right. Well, the polyimide is being used primarily because the 260. So if I go up here, the polyimide has a T sub G of 260. So it means you could take that stuff to a 280-degree lead-free requirements, and it's not going to affect the board material. But then the next question was, let's go down here and say moisture absorption and thermal conductivity, excuse me, water absorption on the polyimide glass is 0.8%. Does that present an issue? And the answer...
We used to make helicopter parts out of polyimide.
Okay.
And we had to cure them for a month.
Yes.
We had a month-long cure cycle with different temperatures to get the moisture out and get their properties where we need them.
Exactly. And so my comment is, if your board shop that knows how to process polyimide glass, the first thing they're going to do is they're going to bake that after every operation, because they're going to make sure that there's no residual moisture in it. Now, the other thing they're going to do is they're going to put a solder mask on that board and completely seal that surface, so all that's exposed is going to be the edges and where you have the components. And so they're going to seal it, so there's making sure that no additional moisture gets into the board during storage, packaging, and over the life of the product.
I think I'm putting together is really, really expensive. A lot of time, a lot of process.
Yeah, by the way, I say polyimide. I don't know if you guys are familiar with flexible circuits that are made out of Kapton. I'm thinking you guys at GatesAir don't use any flex circuits, but that's a major problem with flexible circuits as well. It's a polyimide film, and it picks up moisture like you wouldn't believe, and you have to go through all kinds of operations, and so typically you never see a polyimide circuit. By the way, a flex circuit is like, you look at the hinge on your computer, that little circuit board that's in there that goes from the control board up to the display, and it flexes and bends. That's a typical flex circuit, and you'll never see it without a solder mask or a conformal coat on it, because it picks up so much moisture that if they had it exposed, I'm not sure exactly how much it affects the life of the board, but it affects the electrical performance and also the life of the board. So I don't know, any other questions that I can't answer? Somebody always said when you ask that question, you're supposed to count to 7 or 8. What is it? 8? So let's count to 8 to make sure that that somebody has enough bravery to stand up and ask a question. So I counted to 8. Nobody asked questions. So anyway, so I was going to go on and say materials that that Harris Broadcast or GatesAir has been using, and I can think that TLX was a very large user. If we go back to all those other charts, they're still using a lot of it, but hopefully on new designs, the newer materials that have been developed over the last 5 years are better. Even though this TLX material was developed back in 1966, it hasn't gone away. We're still selling it after, wow, 40, almost 50 years. Still selling it after 50 years. So it's still a very, very large user in our industry. Anything we developed seems to never go away, because once you design it into something, especially if it's military, you can't change it. You can't design it out. So anything we developed back in the 60s, 70s, 80s, 90s, all those materials still exist. The Dielectric 6.15 is something that is also used primarily because I don't think you guys use a lot of that. Some of it. Right, and that's the next one. And the reason that you do this, again, as we go up in dielectric constant, the board size shrinks. So if you had a board which was, I'm going to call it 18 by 12, if you did that same board on a DK of 6, you could probably drop it down to maybe half its size. But there's a lot of other factors on why you don't do it, but that's one of the advantages, at least going to a higher DK. What we did in our industry a lot is always trying to figure out how to improve materials. In the mid 80s, a lot of people were complaining about how to build boards, and the Z-axis expansion was so high and the material was moving so much that they couldn't effectively build good boards and get good plated through holes. And so what we found is that by sticking silica, regular pure beach sand, into the material, we could actually change the mechanical properties of the material without changing the electrical properties very much. And so, as I say, so it's been since the mid-'80s, we've been making these ceramic-filled, silica-filled Teflon materials. So we're taking the silica, mixing it with the Teflon, and then coating that onto the glass fabrics that we then use to make the board. And that lowered the X, Y, and Z expansions in the material and made it more attractive. You could do plated through holes much easier and not have to worry about high temperature exposure in the materials and what it's going to do on the making the material move or making the holes less reliable. So I think you just mentioned, George, that you use a lot of the RF35, which you've used a lot on power amplifiers that you guys are making. By the way, I want to tell you guys, the funny story is that in the telecommunications industry, there are power amplifiers. When you look at every single cell tower, there's power amplifiers at the base of the towers. And so throughout the industry, they're using, well, power amplifiers. And so you go into, Motorola, Ericsson, and you guys, and you say, well, they say, well, we're going to really high power on next design. And I say, well, okay, what are you going to? We're going to go to 13 watts. And then, then we talk to you guys about, well, we're designing a 5 kW, power amplifier. So it's all relative in the industry. But I always laugh when those guys talk about they're going to 8-watt power amplifier.
George, go to RF60. Can we produce our UHF pallet size?
Yeah, we can double the efficiency.
Notice, I say trade-offs. You can go, you'll shrink the size of the board, but then you have to look at the other factors, the dissipation factor, the losses in the material, and the dielectric constant. George has this wish list that he's given us over the years of materials that he'd like us to develop. It ends up being copper-clad air, and we haven't figured out a way to get the bond strength up yet. But to meet his requirements, that's what we have to make. Silver-plated air, right?
Silver-plated copper failure.
And then the other thing, which we just talked a little bit about before, was the thermal conductivity, and it's an issue that again, it does make a difference. Even though I'm sitting there going, if we can take the thermal conductivity from 0.24 watts per meter per degree Kelvin and raise it up to 1, it does relate to a lower running board, a cooler temperature on the board. And so actually, probably it's only been a couple years now, so I'm thinking, well, 2010 was I have on here. We started looking at other fillers that we could stick in the material, like take a little bit of ceramics out and put some aluminum oxide in the material. And so we now have some materials which, and this is not just us, but our industry, people are using aluminum oxide, and that changes the thermal conductivity without drastically changing the electrical properties of the material. And so now this is the one that you guys are starting to use. The second material here, or the first material, RF35 TC, it's the same as the material that you've been using a lot of over the last 15 years, and I think this past year you just started using RF35 TC. And I think we and GatesAir are still going through learning curves. Because there are some issues. It's a softer material than typical FR4, and so I call it the abuse that your assemblers use to stick an FR4 board into your cabinets causes our board material to what do you call it? Be damaged. That's the best way to put it.
The copper peel.
Actually, the edges when they slide these boards, you slide the boards into the rack. The corners of our material is a lot softer than typical FR4 material, so when they jam the boards in there, and I say, well, jam them in there a lot easier. But they typically, completely destroy the edges on the board when they're assembling the cabinets. And so there's some learning curves that your assembly shops are learning with the material because it's different than the FR4 materials that you're using in the past on some of these power amplifiers. And then we also then developed the Dielectric 6.15, which is pretty nice material as far as thermal conductivity, and we raised that from a 0.3 to a little over 1. It's again nowhere near what copper is, but it's a very, very good low loss material and good for shrinking. So he could get some advantages on going to the RF60 TC to get the pallet smaller.
It's a requirement now, George.
So I want to change the subject. You know, there's another thing of, okay, when you're building a power amplifier, what's important? And you pick the dielectric material, and you want a material with a very, very low loss, so you are not generating as much heat. Because remember, I said the fields are going through the material, and a lot of that is generating heat, which is causes, you know, the loss is generating heat. So if the board runs cooler, higher thermal conductivity helps. The lower the dissipation factor in the material helps. But and so that the board will actually run cooler. You can run more power through the board. But also the copper that is used on the board. There's all different types of coppers that are available. And you know, from electrodeposited copper, rolled copper, and by the way, I think I even put in some things here on how all those different coppers are made, and so we could go over that. But one of the things that I note, and when I look at broadcast equipment, you want thick copper to handle the high power, but at the same time, you want smooth copper to get higher RF energy. So the second line here, smoother copper allows for a cooler running board. This is an interesting issue, is that when you look at how copper is manufactured, let me see how far this is. Yeah, let me do this. I'm going to talk about how copper is made, and then we'll come back to, you know, what you guys are using and what you guys are doing. There's a material called rolled copper, and that's typically the copper that's used on flex circuits. And we say it's rolled. How they manufacture it, they take a copper billet and they draw it down between large rollers. And as you roll it down, just like when you're making cookies with a rolling pin, keep on rolling it, the dough spreads out. In this situation, the copper spreads out to an 18-inch wide, 24-inch wide sheet, and then the copper is then reeled up on a roll at the end. The surface roughness in that copper is basically the roughness of those last two little rollers that it hits. And also, if you think about it, the grain direction, because it's a rolling process, the grain direction tends to be parallel to the panel. So that means it's really good for those hinges on a printed circuit board on your computer. It's, you know, it's very ductile. It'll be very, very compliant and bendable. Electrodeposited copper, by the way, we get this copper, we get it in a roll, we actually take it and sheet it. So we cut it into sheets and we put it on the material that you're buying. Electrodeposited copper is how they're manufacturing at the mill. They actually have a very, very large stainless steel drum, and what they're doing is bombarding that drum with copper. And so if you can imagine this drum, well, there's two sides of the copper. When they manufacture it, there's the smooth side, which is right against the drum. Then there's the outer side, which is, I call it, looks like the Himalayan mountains, because it's really very large peaks and valleys in the copper. And again, they roll it up, they ship the roll to us, we take it and sheet it. And traditionally, there's only been two coppers that are available, rolled or electrodeposited, standard electrodeposited. And ED copper, if you can imagine, the grain structure is perpendicular to the panel. So it's not good dynamic bending. You can't crease it a lot, it'll crack. So, you know, so this next picture, if you look at the bottom pictures, actually right at the bottom, you can see that the coppers, you can see there's a tooth, and how typically we stick the copper to a material, and this is true on FR4, polyimide glass, Teflon materials. We are relying on this tooth on the bottom of the copper to grab into the dielectric material, and that's how you get a bond straight. So there's no glues involved. We're actually taking, in our situation with the Teflon, we're taking our Teflon materials up to about 900 degrees Fahrenheit, melting the Teflon, and under very high pressure, melting the Teflon into the copper surface. So we're relying on this tooth in a lot of ways to make sure that we get good adhesion. And so you can get, you know, starting on the one side here, you can see it's very, very rough. There's a lot of, I call it granules or teeth sticking down. And as you come across, you can see that there's, you know, on this, my right-hand side, your left-hand side, it's smoother copper. And now this is where I always sit there and say, the really smooth coppers that are being made today are only 1/2 ounce and 1 ounce. And you guys specify a lot of 2-ounce copper. The issue with 2-ounce copper on the boards, because you want higher power level, is that they're very, very rough. And so I always sit there and say, we've got a problem here, because in order to get the lower loss, higher RF power dissipation on your boards, you really want smooth copper. And 2-ounce copper does not come smooth. It's very, very rough. So I always sit there and I try to convince people in the broadcast industry they should actually buy the smoother copper, 1-ounce smooth copper, and then have the board shop plate the copper up to the required thickness, rather than buying the thick copper from us. Because if we put the thick copper on to start with, it's a very rough copper. And I think you can get better performance if you went the smoother copper to start with, and have the board shop plate up the other, 1 mil, 1.5 mils of, plating on the copper.
The temperature conduction, the heat conduction of the copper, by increasing the cross section of the line, we see that it improves.
Yes, well, but by going to thicker copper.
Yeah.
Well, that's true. So that's why I say you want thick copper, but I don't know if plated copper is any different than as received copper when you look at resistivity. And so, but that is an issue. And so, in fact, what we're doing a lot is we're supplying a lot of, I call it reverse treated copper. When I was showing that picture, I'll switch back here to the drum. There's two sides of the drum, and everybody relies on the tooth of the copper to make it stick. What we've been doing now for a number of years is we're actually taking the copper and we're actually laminating the smooth side of the copper to our material. And so we're putting the tooth up. And so it's a little tricky because it does affect bond strength, but we've worked through that, and I think our expertise is we figured out how to get really smooth copper to stick to our materials. But what it also does, and I'll switch this one. When you're making, I call this one here on the right-hand side, it says standard foil. When you're etching standard foil, you're actually, this is the tooth on the top. You can see where it says C stage. There's the tooth, and you're etching it from this direction. And this is the drum side. And the drum side, it's like a skin, is the best way to put it. And so when they're etching through that skin, it doesn't etch uniformly through that skin. And so what you end up having is a trace that doesn't look rectangular. It basically looks like a trapezoid or like an hourglass. But and with the reverse treated foils, again, they're smoother. And what we're doing is we're actually putting the smooth side against our material. And now when you're etching, you're actually etching through the tooth. And so I look at it and say, it's like calving a glacier. The etching chemistries get right down through the cracks and crevices in the material, and it actually etches away like they say, like calving a glacier. It actually shears off very straight. And so one of the things about microwave is that we're always concerned with coupling what one trace. By the way, you guys have seen microwave boards. When you look at a regular digital board, you can actually look at point A and point B, and you can follow the trace. It goes all the way across the board. On a microwave board, none of the traces go anyplace. They go halfway across the board, and then there's a gap, and then it couples to another trace, and then it couples to another. There's no continuity. And so you're always concerned with how far this trace is from that trace, because the energy is jumping from one trace to another. So there's not electrical continuity, but it's microwave continuity. And so I always ask people, when you're doing a microwave board, what's the distance between this trace, the distance between that trace and this trace? And so how do you measure that? And it's very, very difficult, because you measure foot, you measure the top, but it affects the coupling on a board. Whereas the reverse treated foils, which are smoother, they etch very, very straight sidewalls. And I sit there and say, to me, it's a lot easier to figure out this distance, and it's always consistent. Whereas this always changes, because it depends on how much time it takes to etch through that skin when you're etching the boards. So anyway, I have a lot of different things here, but I'm going to open up the questions if anybody has any questions. And like I say, I can talk for 10 hours. They'd have to bring in dinner. And so, like I say, we've done a lot of work. In fact, I was going to say, this is one thing too. Maybe I will show you this, because what we're doing now, this is a picture of. Let me do this one first. Yeah, this is a good picture. I don't want to say competitor R, but maybe some of you guys knew who that is. But this is a cross section of a piece of material. So this on the bottom portion is the picture of the material. This gold line running across, it's actually the copper trace, and you can see the on the bottom the tooth of that copper and how rough that actually is. And by the way, this is important. And I didn't even mention it before when I was talking about it, but we have this thing in the microwave industry we call skin effect. As the frequency goes up, the current does not run in the trace. It runs on the trace. So for example, at 2 gigahertz, all the current at 2 gigahertz is running in 30 microinches of the surface of that conductor. So if you look at this trace, it's just like to say at 2 gigahertz, 30 microinches, and you think about it, that's not very thick. So the rest of this copper is irrelevant, all the copper trace, when all the signal is running right here. Now think of this as being a bicycle, somebody riding a bicycle, and really small bicycle, and he's going to ride it along here. He's got to go up and down every single hill, every single crack. So one, it's going to take longer to do that because he has to go up and down all the hills and cracks and crevices and valleys, and so it's going to mean more losses. The board is not going to be as efficient. And so this is, I always show this because I sit there and say, this is a very, very high usage competitive material. And so this next picture, I'll go back to, I think, nope. I'll go back to this one. This is a piece of our material with reverse treated foil. And same magnification, by the way, these pictures are identical with different lighting. But you can see, this is the material, what you're looking at here. Ours is glass reinforced. So this is a glass bundle basically coming straight at you. And the line going across is a glass bundle going across the material. But this is what I want you to note. This is the reverse treated foil, same magnification. We're about 1/8 the different surface roughness compared to competitive material. So we can give much, much lower surface roughness. And when you look at the skin effect and how much the current is running on the trace, we have a much, much lower loss on material than other materials. What we're doing now is this is a newer material this is copper foil. And again, this is a glass bundle. This is a glass bundle coming straight at you and a glass sleeve. But these are now the newer coppers that are being developed that we're now shipping to customers. And this is, well, HVLP, hyper very low profile copper, because somebody in the copper industry couldn't figure out what else to call it. And you can see this is at a 500 magnification, and the tooth is getting much, much smaller. And then this is the newest one that we're using now and shipping, and it's called ULP. That's what we call it. The company who makes it, they call it A&P copper, almost no profile. And it's electrodeposited copper, so it etches very straight sidewalls, but there's absolutely no tooth. So what you're looking at here is a copper trace, cross section. So this is the bottom portion is a picture. That big thing here is the copper, and then the shiny thing is actually the top of the copper. But you're looking at this black line. There's actually no tooth to it, which means it's a very, very good material for high frequency applications. And so these are the new things that the industry is developing for the marketplace as things are going faster and faster signal speeds, and people need smoother coppers. So anyway, any more questions? Somebody just pointed at the clock.
So with the reduced tooth, and it's harder to bond that with Teflon. Do you have to find like a delamination, I guess, or is one of the failure mode of that be? Or?
Yes. And so what I think is what sets different companies apart is how they get it to stick. And so, for example, we have spent a lot of money, and I jokingly call it's our Colonel Sanders secret recipe that we use, because we're no longer relying just on the tooth of the copper to bond. We're actually doing a very, very, very proprietary process on our materials to get a molecular bond as well. So we're not just looking at mechanical strength, mechanical tooth. But that is an issue. And so, we have been able to attain 4 to 5 pounds bond strength. And I have another slide on my computer, but we have boards that we've built with 2 mil lines and spaces across a 24-inch board, and they all stayed on the board. And again, 2 mils is pretty small lines. Now you guys never will try to attain that, but when you start looking at our industry, the high-speed switching industry, where like Yahoo and Google, they want very fast signal propagation. They want very, very small lines so they can do a lot of stuff on their boards. And so they're looking at very smooth copper. And so we can actually hold the 2 mil lines and spaces across very large panels without the copper coming off.
Less property dispersion, is that right? The phase velocity will stay.
Yes, and so yeah, in fact, like what the question was, is the phase velocity and everything stays very constant. The issue is when they're doing a design, and you guys do the same thing. When you have a 120 mil wide trace, you don't want any nicks, dings, scratches, anything on that, because you want to maintain a controlled impedance across the board. And it's the same thing when those 2 mil lines and spaces. They don't want 2 mils plus or minus a half a mil. They want 2 mils with no dings, scratches, nicks. They want a very, very straight sidewalls all the way down the whole trace over 24 inches. And these new coppers, you can get that with these new coppers. Also with a good board shop. So
you mentioned the defense industry says they can't apply Roughness, but with all these new materials things, what really is the driver there that doesn't allow them to beat performance?
I think the issue is, you go back in history and you've been around a while, what affects performance on the board? Well, I look at some of these people in this room I've been in this industry longer than some of these people have been alive. And, so when you look back and you go back and tin whiskers, you remember that? Well, we had to go with tin whiskers for years. And so that's what the issue is that what happens as the boards are getting more dense? Tracers are getting closer together. The chemistries, in our industry, in the microwave industry, we call it high frequency shorts. You build a board and all of a sudden you get, you have DC, nothing shorts out, but you put it to RF energy and you get these high frequency shorts in the board because the fields it looks like a short. And why is that? Well, there could be growth from the plating, the copper could be oxidizing, all of that, or the chemistries that are etching chemistries still stay on the board, and all of a sudden over time they sort of like wick through the material, either along the glass bundles or around the ceramic particles, or around the different fillers that are used in the material, and all of a sudden 3 months from now you get shorts in the board because the chemistry is wicked across. And so what the people are finding is that some of these platings are not good. They're whiskering, they're oxidizing, and just the higher temperature. You're taking a board which we used to process at 220 degrees centigrade, and you're now taking up to 280 or 290. And there's a lot of stuff that happens in the board when you look at all the different materials, the pre-pregs or the different layers. That's what causes boards to warp. One layer is expanding this much, the next layer is expanding this much, and eventually you get it out of the IR reflow, and the board looks like a Lay's potato chip. And so that's what I say. All the companies are really sifting through what's the best process, what's the best treatments, what's the best board shop to build the board to meet their requirements. And every company, like I say, Northrop Grumman has completely different requirements than General Dynamics does. And so it's a lot of it I call is really working very closely between the OEM and the board shop. And that's one of the things I think with GatesAir, we deal with probably, I'm thinking of maybe 5 or 6 or 7 different board shops that you guys use around the world. And so we're constantly working with your board shops that you choose to make sure they know how to process our materials so you get good yields when the boards go to the assembly shops and the boards eventually get back to your assembly areas here. And so it's not a simple fix, I guess is the best way to put it. It's a lot of collaboration between us on the materials, the board shops building the boards, what plating systems they're using, what drilling systems they're using, how that affects, when they drill the hole, how clean the hole is so we don't get chemistries penetrating into the material. So it's a very complex dynamics, I guess is the way to put it. So, hey, nobody grabbed the hook and dragged me out of here, but I think we're finished, right?
have to extend a special thank you to Ed because he rearranged his schedule to be here today. Very busy. We have a schedule in one day. And I appreciate that very much. So, yeah, it's there.
Well, thank you. Any questions from Quincy? Seven. Yeah. Okay. Well, thank you. Yes.
Which one of your materials has the similar CTE to copper, or closest?
The reason I'm going to say it's a loaded question, because the CTE matters typically on high modulus materials that are stiff. And so FR4, you should always ask that on an FR4 material, because FR4, once it's cured, it's a thermal set material systems, and the modulus never changes. It remains a stiff material, and the material modulus never changes. When you look at Teflon material, I don't know if I have it on here. When you look at Teflon material, nope, I don't have it on here. Our material is a thermoplastic, which means that as you heat it up, it gets softer. And so the amount of stress in a plated through hole is significantly reduced because the modulus of our material at room temperature versus IR reflow temperatures is like 1/100th of the value. It drops significantly. So our material softens, and so the copper that's in the hole actually drives the reliability of that hole. Where on FR4, the stress goes right to the copper because the material is so stiff, and so the material is really heavy, and it actually takes the copper and stretches it, where our material will actually conform to what the copper's doing. So, I don't know if that makes sense to you, but there's companies, that actually hire thermomechanical analysis engineers to figure out what the board is going to do and what the holes are going to do and what the, putting all these different materials together in a large phase array radar, what's going to happen when it's subjected to high temperatures and environment. But, and so our materials, typically the newer materials now that are high ceramic filled, are typically have lower CTEs. So, but in copper's it's 16.7, and there's very few materials that have the exact same. But it's not a really big issue, in my opinion, on thermoplastic materials. So, so I don't think that's why I say it's a loaded question, because I don't give you an answer because we don't worry about that on our materials.
And an off-topic question.
Yes.
How many pairs of running shoes did you go through on a 100-mile run? And what's your favorite brand?
Oh, well, right now, the guys, I come down here a bit, so I work with the microwave. I run a lot, and so I actually, I finished my first 100-mile race last November, and so I do ultras, and so that's why. And typically, I went through 3 pairs of shoes during the race because over 100 miles, everything expands. I mean, you swell up, and you think, well, I didn't drink enough water. Well, the problem is when you overhydrate, you swell up. When you're dehydrated, you swell up. So during a race, your feet, a 100-mile race, your feet actually grow 1.5 sizes. So the pair of shoes you start with, 75 miles, boy, their feet are really tight. So I just did a 50K this last weekend because the racing season is starting again. But no, I have a couple 100 miles coming up in May and June. But New Balance is the ones I like. But Hoka's are really nice too, but anyway. And my kids run too, so I chase them around. And they run a lot faster than me. I'm old. So, we're good.
Thank you.
Thank you, George. Thanks.